Hello guys, welcome back to Digital Electronics course. In today's session, we'll be talking about inverting inputs and outputs. Um, we talked about inverting inputs before, and then we talked about inverting outputs also. And today we will be adding those two concepts in one lecture and see how we can go from there. Uh, what does that mean? We have to invert we will to invert an input. That means we will add an inverter to the input side of a logic gate, and to invert an output, that will mean to add an inverter to the output side of the logic gate too. Let's start with an AND logic gate, AND 2. So we will add a inverter to the input side of that, and we will see what logic gate we get, and then we will add an inverter to the output side of that, the newly generated logic gate, and see what we will get after inverting the output. So let's move on. Example number 1. Okay, so we will do the first part. The first thing first, we will add an inverter. Will be 2 inverters because we are using AND 2. Input A, input B. We will call it A2 and 2. So that is our logic gate, the inputs being inverted. So we talked about that earlier. Just if we add inverters to the AND gate, we will get a NOR gate. Okay, that will be, now we can have that different representation. Bubble, bubble. A, B. So that is not an AND gate, it's not an AND gate, it is actually a NOR gate, NOR 2 gate. I will just say N2, because the bubble here, and what does that mean here? We can rewrite down that one: A naught single bar, B naught single bar, correct? But that is equal to, we have a De Morgan's theorem, we can do that. We talked about earlier, A, B naught, and this will become A plus A or B not altogether not, and that will become, if you redraw this circuit, this logic gate, this will be equal to this equivalent logic gate A, B. So that will be A or, this is a, ignore this bubble here for now, this will be OR gate, A or B, but this, the output is actually not, so we have A or B not, that will become A or B not gate, which is, that's how we are right there. So, but I like the representation of this one, or A naught plus B naught is equal to Y. Okay, so that is the input after inverting inputs. Now we will add one more inverter to the output side of this logic gate that we just created it. See what we get. So what will that equal to? Change the color here so we know what is going on here. So we inverted the input side of the AND 2 gate, we got NOR 2 in logic gate, and then we invert the NOR 2 logic gate and see what we get. Okay. Sorry. Alrighty. So let's draw this again. A, nor B, and adding this bubble, there'll be, for example, that will be one more bubble here. So that's a lot, just like a representation. This bubble will cancel that bubble, so that will become just a simple OR gate. OR 2, A and B. Input A, input B, and output Y. We cancel those two bubbles out because not will become the same thing like that. A not is equal to A. So A inverted, and then that inverted will become back to this regular signal. So that's how we got this. Will cancel out, it will become, so this was Y naught, and this will, as was adding one more Y naught, so that will become Y naught will become 2Y. So this will be our new logic gate. Let's do one more example here. Example number 2. In this case, we will talk about we will do OR gate. We will add two inputs to the OR gate, and then the new generated gate, we will invert that output side of that gate too. So let's do input to OR gate. To input OR gate, so that will be my OR gate. So A and B, OR 2. I'm writing it down so that we, because my drawings are not that good. So what we get, if we invert the OR 2 input side, we will get what we talked about in the previous lecture. We will get a NAND gate. What we will get, so we can represent that as this. So we have two input, inverted bubble, A, B. So that is not no more OR gate. So what will happen here, we can write down this guy will be A short bar. This is only single bar. Since this is the structure is still OR, we will write down A, B short bar equal to Y, right? This is our Y. And that is also equal to A B will be A and B all together not is equal to this new output. This new logic gate will be, which will be NAND gate, because this structure here is an AND gate, but we inverted that whole AND gate will become a NAND gate. So two bubbles in front of the OR gate will generate or will be equivalent to the NAND gate, or will be NAND gate different representation. This is NAND 2. The output is right here. Not that, I don't want that. Y is like that. Okay, so that's our new representation, and we will see these things as, again, I was saying, don't worry about it right now. We will talk about the Boolean algebra when we go to the Boolean algebra and De Morgan's theorem. We will discuss this in a good details. This is a NAND gate 2, NAND 2 gate, and this is a NAND 2 gate 2. So these are exactly the same, but in a different representation. Okay, in example 3, we'll be discussing how to add we will add two inverters to the NAND gate that we just created here. Two inverters are added to the NAND gate. So our new logic gate will be, so we will not touch that output bubble right now. So we have two bubbles added to the input side. So we'll be having A, input B, and input A, and that is still output Y. So that will be our new logic gate after adding two inverters to the input side. Remember, we still have a inverter to add it to the output side of this. So we got this logic gate. Previously we talked about if we add two inverters to the AND side of the logic gate, and we get a NOR gate actually. So this part is NOR gate. Okay, A and B, but we have this inverter still right there, and this inverter, this bubble and this bubble will cancel out. So this will be A or B, so that will become OR 2 gate. So this is actually an OR 2 gate. Good. Now that was the only input side. Now we have to add inverter back to the output side of it. So when we add an inverter to the output side of it, we will get when you invert the output side of OR 2, we will get a definitely a NOR gate. NOR 2 gate. We can write this new logic gate, which is NOR gate. We will be A or B NOR, or we can call it A NOR B is equal to Y. But if we have this kind of NOR gate, which is inverted bubble inside the input A, B, this is a NOR gate 2. This is NOR 2 also. But we can't write down this one as that representation. We will have to have this one. A not B not equal to Y. And then it's a different case. We can convert that using De Morgan's theorems, and we will write down this one like that. But we can write this as this function. So A naught and B naught, or A and B is equal to Y. So that will be for this logic gate. Hope it wasn't that bad. Please go and review these all three parts of these lectures for this logic gates: inverting the inputs, inverting the outputs, inverting inputs and outputs again. So hang tight, guys, and make sure they review these logic gates if you want to learn more about it. In the next lectures, we will be talking about how to create a function, how to create a function using the truth table. From the truth table, how we will write down a function, and also we will combine some logic gates, and we will have some good stuff ahead of us. So before we start there, we need to review our basic logic gates, which is AND, NAND, OR, NOR, XOR, and XNOR logic gates. And also it wouldn't hurt to study about buffer and the inverters also. Until then, I'll see you guys. Please be careful.